Not yet. Okay, let me show you this one example on the calculator. Everybody look at this with me real quick, please. Okay, sine of 1 over x. I didn't get a chance to finish going over this with you guys, so let me do that. If you want to check this limit, I think the limit was x approaches 0. So I think the problem was, let's consider the limit. That's not a good color. I'm going to fix this. The limit as x approaches 0 of sine of 1 over x, as I believe the example was, that I wanted to really illustrate with you guys. Because when you go to this example, when you try and do the limit with your calculator, you go second. A lot of you would miss this one. Don't worry about Moodle yet. I'll go there in a second. So you go 0 for the limit value, or table start at 0, and then delta table 0.001. Then you go to the table. And what I want you to see is the huge ambiguity that you're going to see on this problem. So if we're wanting to figure out the limit as x approaches 0 of sine of 1 over x, some of you are going to look at the table and be like, I don't know what it is. Okay, so let's move up a little bit so I can see from the left and right. So I've got some values there. I've got an error at 0. Okay, that's a problem. But then you look at it and you're like 0.8733. Okay, talking about from the left. 0.97053. So right here. Okay, then negative 0.3188. Then it goes positive 0.4677. Then it goes negative 0.8269. So it seems like it's kind of bouncing back and forth. What did we talk about yesterday when a function bounces back and forth? We call it oscillating. Okay, so it seems like it's oscillating, right? And then you get on the other side and you're like negative 0.8733, negative 0.9705, 0.1318885, and so on. It keeps like bouncing back and forth between this positive and negative value. So what's the limit? Well, some of you would say, well, maybe it's 0, maybe it's D and E, I don't know. So then you would want to further investigate. So when I graph it, here's the problem. Watch what happens here. And it does something really weird there in the middle, right? So it's hard to tell what it's doing. So here's what you want to do. You're like, I still don't, maybe it's 0, I don't know. So then I zoom in. What am I hit zoom? Go to zoom in, number 2. What it'll do, it'll ask you where did you want to center your zoom. I'm going to center it at 0, 0, because that's what I'm interested in anyways. Hit enter. Watch what happens.
Oh, so it approaches teleports.
Right.
Negative 1 and positive 1.
The closer I get to 0, the closer it bounces what?
Apart.
More, it bounces back and forth. Watch this. I'll zoom in again. That is an indecisive. That's an indecisive person.
Why does it do that?
Because it's an oscillating function. So what do we put here? We're gonna put D in it. That's another. IDK. No. You definitely put D and E because we can't determine what this thing is approaching. It's not slowing down. The closer it gets, the more erratic it gets. Okay? It's like a crazy. I'm on video. I better not say too much. All right? It's just a crazy person. Right? They're just erratic all over the place. It's just bouncing up and down. And the closer you get, the more erratic it becomes. Okay? So that would definitely be any. And I wanted to talk about that because I didn't get a chance to talk about that with you yesterday. So sometimes you have to observe a little bit more than you would like. All right, so go to Moodle, and in Moodle, it's tonight's homework's limit quiz practice key. The notes, oops, I hit them. I don't know why I hit them. Are right there, finding limits analytically notes. Go ahead and click on that. The homework tonight's this one practice worksheet and this. I think what I'm going to do, the Orange Book work, I'm going to wait till Monday, but I'm considering if I get time this weekend, I'm going to make a video to go over the homework so we can save some class time because we really want to get this all done before Christmas. And then what I'll do is make a video and answer questions from the homework, and I'll just go through each section and kind of do a couple problems so you can look at it. But that would require you have to watch it out of class, which I'll just make an assignment for you to watch it in class. All right, here we go. Finding limits analytically using algebra. So we've went over 2 techniques. So I'm just going to get to the intro, and then I'm going to give you a light weekend, and then Monday we're going to come and finish this up. So I'm pretty much going to use the whole hour on Monday to teach and finish this up. I need to, okay, because it takes that much time. We went over 2 techniques, and you just took a quiz on it. You found limits using the graph. You found limits using a table, using your calculator, and looking at the numbers. So besides looking at it graphically and numerically, what we want to do is look at it analytically, which is using algebra. All right, the first thing that and you probably read some about it in the orange book, was this right here, this idea of direct substitution. So what I want to do is introduce what direct substitution is. And you're going to be mad, because you're going to realize, wow, if I would have known that, that would have been really nice. Okay?
Yeah, but sometimes with substitution,
It doesn't work.
Yeah, you get a zero in the denominator.
Yeah, and that's a problem. We got to talk about that. And as we do this, we're going to keep adding more and more things to it as we go through these notes. And in 3 days, we're going to have about 10 to 15 different ways we look at a limit to be able to evaluate it. And you got to go through that whole process to be able to kind of nail down. Now, I've gotten so good at these, I do it so quick, I can get through those 10 to 15 different approaches in about 20 seconds. I think about it all at once. It just kind of happens. I'm like, okay, do this first, and if this doesn't work, I think about this, and I know what kind of limit is. It's a limit as x approaches infinity, so I know there's a whole set of rules for those. And then it's a limit as x approaches a constant, so I know there's a whole set of rules for those, and I know there's shortcuts here and here, and don't worry, you'll see how it all comes together. It actually comes together real slick. I do want you to add some notes to this as you take. So this is super important ante. Okay, I don't even know if that's a word, but we'll go with it. This is very important, guys. If you want to do well on your test, you got to know this backwards, forwards, sideways, slant ways, wonka ways, every ways. Okay, you just got to know it. All right. First of all, direct substitution. This is saying the limit as x approaches c of f of x equals f of c. Wow, what an amazing idea. So what I'm saying is, algebraically, if the function value is defined, what that's really saying there is that you can evaluate a limit analytically just by plugging what x is approaching into the function, and if it's defined, that's what the limit value is. But it has to be defined, because f of c represents some defined value, that point is actually there. Now let me illustrate this, and the best way I can do this is kind of go through some basic limits and hopefully explain this idea of direct substitution. And this is going to be your most important step of evaluating a limit. And what this is suggesting is that direct substitution, one of the first things you're going to do when you look at a limit problem that says find the limit, you're going to try to substitute first. And what do I mean by substitute? That little old principle you learned in 7th and 8th and 9th grade where you just plug something in. You're going to plug it in and see if it works. And if it works, you're done. Let me show you why you're done. Okay? Let me show you why it works, why this direct substitution even works in the first place. It's awesome, and it really comes down to these 3 basic limits. So I want to illustrate these. So let's look at these, each one, and you might want to draw something with each one. Let's look at the first basic limit. The limit as x approaches a constant. Now remember, keep in mind the whole basic idea of a limit is still this. As x approaches a certain value, you're trying to figure out what that y value is approaching. It's not figuring out what the point is necessarily. It's not figuring out what the hole is. It's not figuring out where the asymptote is. It's asking the question of, as x approaches a certain value, as x gets closer, and it's like me moving around. If I walk around the room and I say, who am I approaching? You guys eventually are going to say, but when I was far away, it was hard to determine that. But as I got closer and closer to Joe, you say, well, I'm approaching Joe. How close can you get? You can actually get there. If you can get there, that's great. The closest possible is to actually be there. But the idea is not what it is. It's not whether or not you can get there. The idea is what would be there if you could get there. How close can you get? As close as you want. And the closer you get, what does it look like? What does it seem like those y values are approaching? And you'll get to a point where you just look at it and you'll say, well, I know it's approaching this. I mean, it was like the one where it approached 1 from both sides. It was obvious it was approaching 1 from both sides. Well, it was obvious it was going to infinity on both sides. Okay? Or it's obvious it's going to 0 on both sides. You get to the point where you just look at it and say, well, I know what it's doing. It's going to this. Okay? And that's what you've got to convince yourself of as a limit. But as we do these, sometimes it works out really nice that direct substitution, if the function is defined at that value, in other words, if the point is actually defined at that value, a lot of these problems, when you do them, if that point is actually there, we'll actually not only approach that point, but we know we can actually get to that point. So as I do this, take a look and let me illustrate. So this first one, the limit as x approaches a constant, c, of another constant k. C and k are probably the most important constants, or not most important, but probably the most used letters of the alphabet that represent a constant. C, K, and N. Okay, C, K, and N. Alright? C constant, K constant, N constant. It's usually what they use for constants. Okay? So the limit as x approaches a constant of another constant k is equal to k. Let me illustrate that. Well, first of all, if I take the limit as x approaches c off of it, just look at k. What is k? What kind of equation is k? What would you think of as I looked at that? If that's the, look at this first one. So as I look at this, y equals k, what would you graph? What kind of line?
Y equals x.
It doesn't have an x in it, so I don't know how you do that.
Yeah, but
It's just a constant, so it's a horizontal.
There you go. It's just a constant. I say k is a constant. So y equals k is a constant. So you would graph some horizontal line at k. Now I don't know where k is at. I can put it anywhere. So let's just say k is here. And I graph a horizontal line at k. Now what this is saying, as x approaches c, I don't know where c is, so I'm just going to plop c down here somewhere. As I approach c from the left and the right, the question is, what is the y value approaching? So we actually have to go up to the graph and say, okay, here's the point associated with that x value. And that point is actually defined. Because I know a horizontal line is not undefined anywhere. It's defined for all points. It's what you call a continuous function. We'll talk more about continuity next week, but I gave you a basic working definition yesterday for continuity, and I said continuity is just simply being able to graph it without doing what? Picking up your pencil. Okay, it's very elementary. I could tell a second grader that, and they would get that. Draw the picture without picking up your pencil. Okay, they would get that. We're going to go for a more high school level definition of continuity next week. But for right now, that works. So, as I approach that constant on that graph from the left, and as I approach that constant from the right, we know that we're just approaching that actual what? Point. And what's the y value associated with that x value at that particular point? K. That is why the limit as x approaches c of a constant is whatever that constant is. So say it with me. The limit of a constant is a what? Constant. The limit of a constant is a constant because it's a horizontal line. And we know that y value is always going to be whatever that y value is for that horizontal line. If it would have been y equals 2, then it wouldn't have mattered what x approached. It would not have mattered. X could approach anything, and it's always going to be whatever that y value is. Now that doesn't really give any light into direct substitution yet, but at least you can see, well gosh, if I'm approaching that point, and it's whatever the y value is at that point.
Is that only if they give you f of x then?
Well, we're always going to know what the function is. But whether it's defined or not, we don't know, because you said you ran into some ones where you might get 0 in the denominator. That's a whole other story. Alright, so the first one, limit of a constant is a constant. Now, this next one really, I think, these next two properties, or basic limits, really illustrate what direct substitution is. And let me look at that. This next one, the limit of a constant of x. What is x? Y equals x. What is y equals x? It's the line with a slope of 1. Passes through the origin. There's the line y equals x. What do you know about the line y equals x? It's called the identity function. What do you know about the line y equals x? Give me a special property about that line. Besides the fact that it goes through the origin, besides the fact that it has a slope of 1, what else do you know about the line y equals x?
Right hand after you line
Well, yeah, your shifting all kind of originates from this for a line, like shifting up, down, left, right. You could say symmetry, all that stuff, but I like what Canyon said. You know what? Every point on that line, the x and y are the same. Pick any x value, the y value is going to be identical. Every point, the x and y are identical. You have the point 2, 2, 1, 1, 3, 3, 100, 100, negative 5, negative 5, negative 10, negative 10. The reason we like this is because this really illustrates direct substitution. Because you pick your c value, so I'll pick c, and there is a point associated with that c value. And as x approaches c, we know by looking at this that as I approach it from the left and as I approach it from the right, I'm actually going to approach that point. And since that point is actually defined, all I got to know is what's the y value for that point. Well, what does the y value happen to be if this is the line y equals x? It's just whatever c is. which perfectly demonstrates direct substitution. Because then what I'm saying here is the way you figure out this limit is the limit as x approaches c of x, just plug c in for x and you're going to get c. That is direct substitution in a nutshell. I'm just plugging c in for x. I'm substituting in for that variable. That's what direct substitution is. It's just plugging something in for that variable. I'm saying since the limit is x approaches c of x, to evaluate that limit, if I can plug it in and it works, then whatever you get when you plug it in is the limit. And we illustrate it with this one. Now we can build off of that. So we got our basic atoms. Let's build some molecules. Okay? And then we'll build some compounds and elements and all that junk and whatever it is. All right, the third one represents, okay, well, if I can do it with basic x, what if I do stuff to x? What if I start doing powers of x? Does it still work? And the answer to your question is yes, it still works. So if I go limit of x approaches c of x to the n power, I'm just going to get c to the n. I just literally plug it in, and it's just going to be c to the n power. Perfect example of that would be the parabola. Let's just do a simple parabola. And let's do the limit as x approaches 0 of x squared. Now, looking at the graph, most of you would agree. Hey, look what it's approaching from the left. What does it look like it's approaching from the left? 0. What does it look like it's approaching from the right? 0. So we know the limit's 0. Well, let's see if the algebra works. If I plug in 0, what's 0 to the second power? 0. It works. Direct substitution works.
Last night in 2.1, it like for the powers, want to give like x to the power of r divided by s equals c to the power of r divided by s. What is that?
I'm going to go over that. I'm going to go over that algebra stuff, so don't worry. I'll look at that. Let me finish this up. Let me get through this, and then we'll kind of get a stopping point here. Okay, I got a couple more minutes. Properties of limits. This right here, I'm going to tell you right now. Put exploding candy by it, highlight it, do whatever you got to do. You need to know this inside out, backwards, forwards, blind ways, walkaways, every ways. Okay, you got to know this. These properties are so handy. Okay, and this is where college professors get into really proving limits, and I'm going to do a little bit more of proving limits this year because I'm finding out that the college professors really want you to know not only the shortcuts, but they want you to know how to prove that it works using these properties. And I really will put you in a bad situation if I don't show you how these properties work, even though I know how they work and I love them because they're very, very helpful. If you understand these at a very, very deep level, limits really become really easy. The first one, let me go ahead and tell you what they give. They said let limit as x approaches c of f of x equals L, and let the limit as x approaches e of g of x equals K. So we're saying, here's the limit of f of x, and we're saying it equals some number L. I don't know what it is. It could be 5, it could be 10, it could be negative 5. Whatever the answer is. So we're just say capital L for whatever the answer is. And then we have another function, g of x, and we're saying that answer is capital K. The first property is called scalar multiple. I'm going to get through these and I'll be done. Scalar multiple. It says the limit of a constant of b times f of x, your BFF, b times f of x is b times L. You know what that's really saying? This is a really cool property. It's very useful. In fact, this property is going to help me prove all of integral calculus. That's the second branch of calculus we're going to learn. We're going to learn 2 branches of calculus in here. And it's going to help me prove that second branch that we'll learn in March. And all you do is it allows you, really what this is saying, you should write this down. It's really saying that if you have a limit of some number multiplied by that function, so if that function gets multiplied by 2, if that function gets multiplied by 3, if that function gets multiplied by 10, if there's a coefficient, what you really can do with it is you can bring that coefficient out front. It's really handy. It's really saying you can pull that coefficient, whatever that number is, you can pull it out front. And then just take the limit of the function and then just multiply by b at the end. It's very useful. Allows us to do a lot of things. And you'll see, you'll be like, man, I'm glad we got that. Because if I've got numbers in there, if I've got constants, like if there was a pi there, hint, hint, later on we're going to have a pi there, you'll be able to put that pi out front. Or if there was a 2 there, I can put that 2 out front. Or if there was a 5 there, I can put that 5 out front. And then I can just make the limit problem simpler. I can find the limit, and then in the end, just multiply by whatever that constant is. It's a very handy property. Real quick, these here sum or difference property says you can do the limit of multiple functions that are added and subtracted. So I can do the limit of f of x, figure out that's L, and I can add or subtract whatever the limit of g of x is. So I just take L plus or minus k. And I'll illustrate these more on Monday.
So you can find the limits individually.
You can find them individually. You can find the limit of each part, which really means that we're going to be able to take our direct substitution to the next level. So now we don't have to just do a single term. We don't have to just do powers. We can do powers that are added or subtracted. So now we've got polynomials that we can do the limits of. Products work too. So now we can do foiling. We can do the limits of things that were foiled together. This times this, it'll just be L times K. You can take the limit of each part. This one's really handy, number 4. You can do the limit of the numerator divided by the limit of the denominator. You can find the limit of the top and then divide it by the limit of the bottom. We're going to use that one a ton. Provided, watch this, that can't equal 0. The bottom still can't equal 0. Don't want 0 on the bottom. If that happens, we're going to have to do further things. And then the power one I've really already illustrated. You can do the limit of this. You just did it. You did the limit of x squared. You did the limit of x, you plugged in the 2, and then you squared it. So what it's saying is you can do the power after you do the limit of the inside. Okay? And just to finish this real quick, what's the limit of a constant? So what would the limit of x approaches 2 of 3 be? 3. The limit of a constant is a constant. What would the limit of x approaches negative 4 of x be? You just plug in negative 4. It's direct substitution. It has to work according to this property. And what's the limit of, we just did this one, 2 of x squared? You just plug it in. It's 4.
That would have been nice to know.
Yeah. Well, now I'm gonna reveal everything to you. Okay. See you on Monday.
Except they were all of like x approaches